Okay. Alright, so this is the content for chapter 2, shallow foundation. Okay. The first one is introduction. Okay, introduction about the shallow foundation, how to classify the shallow foundation. Okay, general concept, Terzaghi bearing capacity theory, factor of safety, modification of bearing capacity equation for water table, and the general bearing capacity equation. Okay, so to design the shallow foundation, we will use only two methods. So there are various methods of design shallow foundation, but for this course, okay, you will learn only two method. Okay, the Zaghi method and Meyerhof method. So the general bearing capacity equation is the Meyerhof method. And then eccentrically loaded foundation. So this is the special case where the load is not vertical. Okay, so we will calculate and we will design the non-vertical load. Okay, ultimate bearing capacity under eccentric loading. Okay, one way eccentricity. Okay, and then of course, okay, for foundation you have to calculate not only the bearing capacity, okay, of the soil, but you have to calculate also the allowable or settlement or the limit, okay, the maximum limit of the settlement. Okay, and then last one is the primary consolidation settlement relationship. So this is consolidation is special for clay soil. So for clay soil you have to calculate using the consolidation behavior. Right. Okay, so the shallow foundation. So what is shallow foundation? Okay, shallow foundation represent the simple form of load transfer from a structure to the ground beneath. Okay. Okay, they are typically constructed with generally small excavation into the ground. Okay, do not require specialized construction equipment or tools. Okay, maybe we just need only the excavator, right? Okay, you have to dig the hole. Okay, maybe 2 meter, maybe 3 meter, or maybe 4 meter. Okay, relatively inexpensive because the construction is only less than 10 meter, so relatively inexpensive. It's quite cheap compared to other foundation, such as pile and other foundation. Okay, in most cases, okay, shallow foundation are the most cost-effective choice for support of a structure. So in the design, if you want to design the structure, building structure, you have to start with shallow foundation first, before you go to the deep foundation. Try to design using the shallow foundation first. Okay, you try using pad footing, and then if the pad footing is not capable uh, to withstand the load, so you have to change to maybe combined footing, and then after that try to mat footing. So if mat footing also cannot withstand the load, so you have to use the deep foundation or pie foundation. All right, so that's why shallow foundation is the first attempt in your design of foundation. Okay, must satisfy these two design criteria. Okay, of course, in design of foundation, you have to check. Okay, you have to satisfy the design criteria. Okay, the first one is the bearing capacity. Okay, bearing capacity. How uh, uh, how strong is the soil to support the load from the structure? Okay, from the dead load. Okay, from the live load. Okay, and then of course you have to check the settlement, and then the settlement should be within the tolerable limits. Okay, for example here, this is only the example. Okay, the settlement, the maximum settlement is only 25 millimeter, 2.5 centimeter for isolated foundation or pad foundation, and 50 millimeter for rough foundation or mat foundation. Okay, so this is the example of the shallow foundation. So if you see here, so okay, we construct. Okay, for this example, this is a traditional house. Okay, we just put it the pad on the ground surface, right? But it's still okay because the load from the structure is quite low compared to the high-rise building, right? And then you see here, this is the example of the shallow foundation. So we only dig maybe 0.5 meter below the ground surface, and then we put the reinforcement, and we put the concrete, and we make it the shallow foundation, right? And then this is also the example of the shallow foundation. So this is the combined footing. Okay, this is the combined footing. The combined footing is where the footing support two column. Okay, support two column. Here we have column here, we have a column here. So we design using a combined footing. This is also shallow foundation. Okay, so what is shallow foundation? How to classify the shallow foundation? Alright, the term of shallow foundation, okay, varies from author to author, but generally, okay, generally you can use these notes. Okay, the depth. Okay, the depth from the ground surface to the base of the foundation. Okay, this is the df. Should be less than the width. Okay, this is from Terzaghi, 1943. Alright, but the latest researcher, okay, mentioned that the depth of the foundation is 3 to 4 times of B. B is the width of the foundation, right? So even though the depth of the foundation is larger than the width of the foundation, we still can consider as shallow foundation. Okay. Okay, we have many type of footing. Footing for shallow foundation. Okay, the first one is the spread footing. Okay, where the spread footing is support either wall or one column. Okay, the wall or a column. Okay, the wall, for example, okay, spread footing may be one of the following type. Okay, we have strip footing, we have pad footing. So what is strip footing? What is pad footing? Okay, so if you see here, okay, so this is the simple footing. Okay, one footing support for one column. Okay, one column and one footing, so we call that a pad footing. This is the simplest one. And also we have strip footing. Okay, so this is the strip footing where the length is more than the width. Okay, for example, if you want to construct the retaining wall, for example, okay, so this is uh, the type of straight footing, right? Or if you want to design uh, we call that the wall, bearing wall, for example, the bearing wall. So you can use a straight footing, right? And this is the mat footing or the rough footing. Sometimes we call rough foundation, mat foundation, right? So if you see here, okay, the mat foundation, okay, cover almost the column. Okay, so what what are the advantage of the mat footing, okay, or rough footing, okay, compared to pad footing and straight footing? When we have to use the mat footing, okay, okay, rather than pad footing. Okay, bila kita nak gunakan mat footing? Many columns. Okay, so pad footing also support many column, right? But why we choose pad footing? Why we choose rough footing? Okay, depend on the soil condition. Okay, can you give that? Okay. Yes. The space very small. Okay. All right, the space. If the space is very small, you can use the combined footing, right? Mm. But if you see here, the column here is, and the column here is not too close, right? But still, we can use mat foundation. Okay. Yeah. Yeah. Actually, if you use pad footing, for example, okay, if you choose a pad footing, if there is a differential settlement, okay, for example, we have 10 column, okay, we have 10 column with 10 footing. One footing, the settlement is 10 millimeter, for example, and another footing is 15 millimeter. So means that there is a difference in settlement. So we call that differential settlement. So if the differential settlement is very high, so it will damage the structure. Okay, we damage the structure. We it will crack. Okay, okay, and then maybe maybe the structure will be collapsed. Okay, compare with the mat foundation or rough foundation. Okay, actually, actually, if you use rough foundation, okay, you can reduce the stress on the soil, right? Because you apply into the large area, okay, compared to the bed footing, right? So you have the column here, you have the load here, and load divided by area of the footing, and you can get the stress, okay, the stress under the foundation. So if you compare the total stress here, okay, compare with the stress here, even though you combine with many columns, and you can get, okay, the stress under the footing for the mat foundation is lower than the pad footing. So that's why the pad footing, the rough footing is suitable for low bearing capacity of soil. Okay, so if you have low bearing capacity of soil, then you can propose to use the mat foundation or rough foundation. Okay. And also if you want to avoid differential settlement, okay, so for example here the settlement here is higher than here, all right, so it will crack at the middle of the structure, right? Okay, but if you use the mat foundation or rough foundation, so it will give you the uniform settlement. So there is no more differential settlement. Right, so this is the pad footing, or sometimes we call isolated footing. Okay, support one column, okay, for each footing. And then we have a combined footing. So combine means we combine two columns with one foundation, one footing. Okay, so this is the example of the combined footing. Okay, support two columns. Okay, it is used when the two columns are very close to each other. Okay, so if the column is very close, then you have to combine. Okay, you have to use the combined footing. Or when the bearing capacity is low, okay, when the soil have low bearing capacity, then you can try to use the combined footing in your design. Okay, this is the strap footing. Okay, this is the strap footing. Okay, a strap footing comprises of two or more footings of individual columns. Okay, connected by a beam called a strap. So this is the beam, this is the column, and this is the footing. So the footing is connected with the beam, or we call strap, right? So you see here, this is the example of the strap footing construction. Okay, so we combine with two or more footing, okay, but only support individual columns. And this is the rough foundation. All right. Okay, a rough foundation is a combined footing that covers the entire area, okay, beneath the structure and support all the walls and column. All right. So this footing, this type of footing, support all the load from the column and from the wall. Okay. Right. Okay. See, this is the example of footing, the rough foundation. Okay. Okay. The requirement for the rough foundation, when we have to use rough foundation, okay, rather than strap foundation or uh, pad foundation. Okay, when the allowable soil pressure is low, okay, that means that the bearing capacity of soil is low, or the building's loads are heavy. Okay. Okay, use of spread footings will cover more than one half of the area. So if you use spread footing, and then it's cover more than half of the area, so it's better for you to use mat footing, okay, rather than spread footing. Okay, soil is sufficiently erratic so that the different settlement difficult to control. Okay, so that's why, because if you have the construction area, for example, 100 meter times 20 meter, for example. Okay, if you want to construct the school building, okay. So the settlement from one point to one point is different. Okay, even though the distance only 1 meter or 2 meter. Okay, because the behavior of soil, because the properties of soil is different, so the settlement is also different. So to avoid the difference of settlement, so that's why, okay, we use the mat footing. Right. Okay, to design the foundation, okay, you have to know of course, the geometry of the foundation. Okay, if if you want to design the square foundation, Okay, so you have to know the width and the length, okay, of the foundation. If you want to design the straight foundation, you have to know the B and L. If you want to design the circular foundation, so you have to know the diameter of the foundation. So to design the foundation, you have to know the symbol B and L. B is the width, L is the length of the foundation. And then you have to know, you have to familiar with the term DF, okay? With the term DF. Okay, okay, the term, uh, okay, the term here, okay, DF. So what is DF? So what is DF? Okay, I will explain to you later what is DF. Okay, for the pad footing, okay, for the pad footing, the contact pressure or load per unit area, okay, in kilonewton per square meter at the interface between the pad foundation and the soil is given by, okay, Q. Q is the contact pressure. Contact pressure is the, okay, this is the pad footing, for example, the pad footing. Okay. So you have to calculate the area of the foundation. So the contact pressure is the pressure underneath the footing, right? So if you have 2 meter times 3 meter, okay, footing, so you have to calculate the area here. B equal to B equal to 2 meter, and then L equal to 3 meter. So to calculate the Q or the pressure, Q is the column load. Q is the column load. Okay, Q is the column load. Okay, divided by area. So actually this is the area of the foundation. All right. So actually this is the pressure underneath the foundation is the bearing capacity. We call it bearing capacity. Okay. Okay, for street footing. Okay, street footing. So this is the example of the street footing. Okay. The length divided by B. Okay, the length divided by D almost to infinity. Infinity. Right. For example here, B equal to 2 meter. The length is 1000 meter, for example. Okay, or 100 meter. Right. So that's why we call it the street footing. Street footing. Okay, for street footing, okay, we present the contact pressure in unit kilonewton per meter. Okay, means that we only calculate for 1 meter length of the foundation. Okay, so in this case, the contact pressure Q equal to capital Q divided by B, the column load divided by the width of the foundation only. Okay, because the L here, suppose we have L here, right? But L equal to 1 meter. So this equation become Q equal to Q over B. But if you want to calculate for the whole footing, so you just multiply by the length of the foundation, right? Okay. Okay. In design of the footing of the shallow foundation, so this is actually the factors, okay, influence the bearing capacity of the soil, right? Okay, the first one is the type of soil. So of course, if you compare the clay soil compared to sandy soil. Of course, sandy soil have good bearing capacity compared to clay soil. Unit weight of soil. Okay, the soil with higher unit weight, of course, will have higher bearing capacity. The surcharge load. Okay, the surcharge load, the load from the structure. Okay, uh, the higher the load, the lower the bearing capacity or the factor of safety. Okay, the depth of the foundation. Okay, the higher the depth, the higher the bearing capacity, right? Because the unit weight of the soil will increase with depth. The size of footing. Okay, the size of footing also influence the bearing capacity. Okay, shape of the footing. Okay, shape of the footing, we have a circular shape, we have a rectangular shape, we have square shape. Okay, okay, mode of failure. Okay, mode of failure. Okay, depth of water table. Okay, okay, the location of the water table. Okay, below the ground space will also affect the bearing capacity. So we will see later. So we will check this. Okay, the mode of failure. Okay, and then the depth of water table. How the depth of water table influence the bearing capacity, and eccentricity in footing load. Okay, so I think this is will cover in this course. Inclination of footing load, inclination of ground, inclination of base foundation. So I think we learn this in advanced foundation. Advanced foundation. Right. Okay, so this is the mode of shear failure. This is the mode of shear failure. So actually we have three type of shear failure mode. Okay, the first one is the general. It's the general shear failure. Alright. So general shear failure commonly occur in dense sand or stiff cohesive soil. So if you refer to this figure, okay, figure A and figure B, okay, if a load gradually applied to the foundation, the settlement will increase. So if you see here, this is the settlement and this is the load. So if you apply the load, okay, you can have the settlement. Okay, so the settlement also will increase. Okay, but load per unit area is the contact pressure. This is the contact pressure or the bearing capacity. Right? So when we increase the load, okay, it will equal to QU here. QU is the maximum contact pressure, okay, for the soil. So we call that ultimate pressure. Okay, QU is the ultimate and U is ultimate. Okay, beyond this point, okay, the settlement, okay, will occur, but the bearing capacity will be decreased. Okay, so you can get the Q ultimate. Okay, you can monitor the Q ultimate. So this is actually the general shear failure, and you have to memorize. Okay, actually the general shear failure is for dense condition. Okay, for the dense sand and stiff cohesive material. Okay, okay, because okay, when we apply the load, because the soil condition is dense, okay, so it will dilate. Okay, we will dilate. Okay, dilation. Okay, so that's why there is a dilation here. This is the dilation. uh, at the ground surface. Okay, so this is the case of the general shear failure. Okay, what about local shear failure? So the local shear failure, okay, is for medium sand, okay, and medium sand or medium dense of clayey soil. Okay, so local shear is for medium dense. Okay, general shear failure is for the dense condition. Local for medium. Okay, if you see this figure, okay, an increase in the load on the foundation causes increment of the settlement. Okay, same with the previous condition. Okay, in this case, okay, the contact pressure QR equal to Q1. Okay, here, Q1. Okay, a movement of the foundation will be accompanied by sudden jerks. Okay, after that there is sudden jerks. Okay, so this is sudden jerks. Okay, so there is a settlement here. There is a settlement here. Okay, and then it achieve QU. QU is the ultimate pressure. Okay, this is the ultimate pressure. And then beyond this point, beyond Q ultimate, if you increase the load, okay, the settlement of the foundation also increase rapidly. Okay, increase rapidly. Okay, this condition we call as the local shear failure. Okay, and then the last mode of shear failure is the punching shear failure. So this is the punching. All right. So if you see here, there is no movement of soil at the ground surface. Okay. Okay, and increase the load foundation will also increase the settlement. Of course, if you apply load, so of course there is a settlement. Okay, in this case, the failure surface in the soil will not extend to the ground surface. So there is no movement of water at the ground surface. Okay, and then same with the local shear failure. If you increase the load, there is a increasing of the settlement, and then after QU, after ultimate bearing capacity, the settlement will increase rapidly. So this is we call that the punching shear failure. But in the question, sometime we ask you, okay, to design, okay, according to, okay, for example, general shear failure. Sometimes we ask you to design according to punching shear failure. But sometimes we give you the condition of the soil. Okay. Okay. For example, okay, for medium dense sand, determine the bearing capacity of soil. So you know that, oh, this is the local shear failure. Okay. The condition of the soil. You see here, this is the condition of the soil. Okay, if you want to design the foundation in soft soil, means that the pattern or the mode of failure is the punching shear failure. Okay, or for the loose sand, of course, the punching shear failure. Right. So this is the correlation of the relative density. Okay, this is for sand. Okay, relative density is for sand. Okay, if you see here, if the relative density is maybe 0.35, so the relative density is less than 0.35, so the mode of failure is the punching shear failure. If the relative density is between 0.7 to 0.35, so the type of shear failure is the local shear failure. So if the density, the relativity is more than 0.7 or 70%, the general shear failure will be occur. Okay, so this is the guideline for you to design the foundation, okay, based on the relative density. Right. So this is the Terzaghi bearing capacity. Okay, to design the shallow foundation or deep foundation, this is the important parameters. Okay, you have to know these parameters, okay, before you can design the foundation. You have to know the unit weight of the soil. Okay, either gamma dry. Okay, either gamma saturated. Okay, or you have to use gamma prime, right? So this is the fundamental. Okay, so what is gamma prime? Gamma prime is the effective unit weight. So effective unit weight is, okay, gamma saturated minus gamma water, right? So if you know these parameters, okay, then you can use the Terzaghi bearing capacity. Okay, so if you see here, so this is the equation to calculate the QU. QU is the ultimate bearing capacity. Okay, QU is the ultimate bearing capacity, equal to C prime NC plus Q NQ plus 0.5 gamma B and gamma. So if you see here, you have to know what is the C, the cohesion. Okay, you have to know what is the cohesion. Effective, effective. Prime mean effective cohesion. Okay, so you have to know C, right? And then you have to know the width of the foundation. Okay, the width here, the width of the foundation. And you have to know Q. Q is the surcharge. Okay, the surcharge mean the surcharge from the ground surface to the base of the foundation. Okay, from here to here. So what is the surcharge? Surcharge is equal to unit weight of this material times dF. So this is actually dF, depth of embedment. Okay, from the ground surface to the base of the foundation, we call it dF. So the surcharge is start from foundation to the base of the foundation here. Okay, gamma. Okay, so you have to use gamma, either gamma prime, gamma saturated, or gamma dry. But here you have to use gamma prime, effective unit weight. Okay, what is NC, NQ, and gamma? Okay, NC, NQ, and gamma is the bearing capacity factor. Okay, bearing capacity factor. So what is bearing capacity factor? Okay, here. Right. So this is the equation, okay, to calculate the bearing capacity factors. Okay, NC, NQ, and gamma. Alright. So I think it's quite time consuming, right, to calculate NC, NQ, and gamma. But okay, you can use the chart, the table, okay, to obtain NC, NQ, and gamma. Right. For example here, if you want to if the soil have a friction angle of 20, okay, then NC equal to 17.69, and NQ is 7.5. 0.44, and then N gamma is 3.64, right? So now you know what is NC, NQ, and N gamma, okay, from this equation. Okay, from this equation you know what is NC, NQ, and N gamma. Okay. Okay, actually this table is for the general shear failure only. Okay, for general shear failure. Okay, if the condition of the soil is medium dense, we have to use other table. Okay, you have to use other table. Okay, ultimate bearing capacity. Okay, general shear failure. Okay, to estimate the ultimate bearing capacity of square and circular foundation, the previous equation may be modified. Okay. So this is the equation for continuous or straight foundation. Okay. Okay, so this is the equation for square foundation. QU equal to 1.3 C prime NC plus Q NQ plus 0.4 gamma BN gamma. And for circular foundation, so we have B, the diameter of the circular foundation. So QU equal to 1.3 C prime NC plus Q NQ plus 0.3, okay, gamma BN gamma. Okay, so this is for Terzaghi equation. So for Terzaghi equation, we can use the equation only for circular foundation, for square foundation, and for the continuous foundation. Okay, if you want to design this type of foundation, for example, the width is 2 meter and the length is 3 meter. So this is the foundation. You have 2 meter times 3 meter. Is it possible for you to use the Terzaghi equation, okay, to calculate the bearing capacity of the soil? Okay, anyone? Volunteer to answer my question? Ada nak jawab tak? Hello? Ada nak jawab? Do you want to answer? Can we use the Terzaghi equation? Okay, if you have this type of foundation, you have 2 meter times 3 meter. Boleh ke tak boleh? Tak sure. Okay, I give you two conditions. The first one is 3 meter times 3 meter. Okay, and then the other one, 2 meter, 100 meter. Okay, can we use the Terzaghi equation for this type of foundation? For this one? No. Why? Yes. Yeah, okay. Yes. For the first case, we can use the street foundation. Okay, here. So you can use the Terzaghi equation, okay, to calculate the bearing capacity of this type of foundation. Okay, okay, we go to this one. 3 meter times 3 meter. Yes, because this is square, right? Because this square foundation. So you can use the Terzaghi equation. What about this one? 2 meter times 3 meter. Mm. Is it possible? Not sure. Not sure. Sorry? No, 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 no. This type of foundation. Okay, this is my proposed foundation. I want to use 2 meter and 3 meter. Okay, can we use the Zagi equation to calculate the bearing capacity? Okay, underneath the foundation. 2 meter and 3 meter. 2 meter kali 3 meter. Boleh ke tak? Kalau 3 meter kali 3 meter, okay. Sebab this is square, right? This is rectangular, kan? This is rectangular. It's not square. This is rectangular. But this is not the street foundation. This is not continuous. So we cannot use the Zagi equation for this case. But if you have the footing with the geometry like this, so what you have to do? Split. Split. How? Oh, macam tu. 1 kali 1. Macam mana tu? Jadi 2 macam mana? Bukan jadi 2. Jadi macam tu. 3. Bagi 3 yang tu. 1 meter. 1 meter here, 1 meter here, 2 meter here. 2 meter here. 1 meter. Boleh tak macam tu? This is square, this is square, this is square, this is square, right? Boleh kot. Boleh kot. But it's square juga, Oh. Okay. You will become an engineer. So you have to decide either you can use the Zagi method or not. Okay, but actually, if you cannot use the Zagi equation, okay, we have other method, okay, that consider the rectangular shape. So you can use Meyerhof method, okay, rather than the Zagi equation. Then you can use the Meyerhof method. Okay, because the Zagi equation is very simple. So if you see the equation, the Zagi equation only consider the shape factor only, yeah. The shape factor. Um, not the incline load and everything. So it's very simple actually. The Zagi equation is very simple compared to Meyerhof. Right. So ultimate bearing capacity, local shear failure. Okay, so this is for local, This is for the local shear failure. Okay. Alright, so you have to modify the equation. Okay, from the general shear failure. Okay. So for local shear failure, for the street footing, okay, you have to use this equation. Okay, for square footing, okay, you have to use this equation. And for circular foundation, you have to use this equation. For local shear failure mode, for the local shear failure mode, you have to use this equation. Okay, what about the local shear failure? Okay, for the local shear failure, so this is the bearing capacity factors of NC, NQ, and gamma. Alright, so you have to careful. Okay, either you want to use the bearing capacity factors for general shear failure or for the local shear failure. Right, so you have to read the question first. Okay, either the question asks you to design based on the local shear failure, or you see the condition of the soil. Either it is dense condition, medium dense, or loose condition. Right. Okay. The factor of safety. So of course, if you design a structure, you design the slope, okay, you have to check the factor of safety. Okay. So factor SFT equal to QU divided by Q allowable. Alright, QU is the ultimate bearing capacity. So the ultimate bearing capacity is the maximum pressure that the soil can support. Okay, so this is the maximum. Ultimate is the maximum pressure. Alright, and then Q allowable bearing capacity is the Q design. Okay, this is the Q design. Q allowable is Q design. Q design. So we use this stress to design the foundation. Okay. Alright, for example here, if you want to design the foundation, you have to calculate the Q allowable. This is the Q design. Okay. For example here, Q ultimate 500. Okay, for example, kilonewton per meter square. So if you want to design the structure, okay, you have to design the allowable pressure should be less than QU, right? If the Q, okay, the load from structure is equal to QU, means that Fs equal to 1 because Q allowable equal to QU, right? Okay, so actually it's not safe. It's not safe because when Fs equal to 1 means that critical. Critical. ICU Kalau masuk hospital tu masuk ICU lah, critical. Alright. Either you can save or the structure will collapse. So this is the critical one. Okay, so that's why in most design the factor of safety of 3 is commonly used. So if the factor of safety is 3 is applied to this design, so Q allowable equal to 500 divided by 3. So maybe, okay, the allowable load from the structure is only, okay, 222. It's only 222 kilonewton per square meter only. Okay, so you cannot use 500. Okay, when you use Fs equal to 3, so you have to use only 222 kilonewton per meter square. So this is the Q allowable. So you have to make sure that the load from the structure is less than or equal to 222 kilonewton, okay, per square meter. Right. Okay, so this is the example. Okay, this is the example. Okay, calculating of allowable gross load. Okay, you see here. Okay, the question asks you the allowable. Right, allowable ni yang design lah. Okay, yang kita benarkan. So allowable mean the load Q. Load is capital Q. Okay, a square foundation. Okay, a square foundation means you can use the Terzaghi equation, right? It's 2 meter times 2 meter in plan. The soil supporting the foundation has a friction angle of phi prime equal to 25 degree and C prime is 20 kPa. The unit weight of soil is 16.5 kilonewton per square meter. Determine the allowable gross load on the foundation with a factor of safety of 3. Assume the depth of the foundation df is 1.5 meter and that general shear failure occurs in the soil. Okay, it mentioned general shear failure, right? So you have to use the equation for the square foundation of the general shear failure mode. right? So you want to try? You want to try? Okay, I give you 5 minutes. Okay, give you 5 minutes. Try to get the answer. Okay, for this problem. And then after, okay, okay, we take five. Okay, and then I give you 5 minutes. Okay, to get the answer. Actually, it is survivable in the slide, but we will discuss later. Okay, 5 minute rest. 5 minute rest. Okay, kita sambung. Alright. Alright. Ada tak ni? Ada lagi di sini? Ada. Okay. Alright. So this is a very simple question. Okay. Alright. Solution. Okay, because this is the square foundation. So, and then the general shear failure. Alright. So, okay, we can use this equation. Q ultimate equal to 1.3 C prime NC plus Q and Q plus 0.4 gamma B and gamma. Okay, from graph. Okay. Okay, for friction angle 25 degree. Okay. Okay, so we get 25.13. NQ. Okay, so we get 12.72, and then N gamma is 8.34. So this is the bearing capacity factor. And then C. So we have C here. C is 20, right? Okay, C is 20. Q. Okay, Q is the gamma DF. Okay, gamma is 16.5. Okay, DF is 1.5. Okay, so 1.5 times 16.5, and then gamma is 16.5, right? Because the given unit weight if is in dry condition, so we just use this value. But if the soil is saturated, then you have to calculate the effective unit weight. Okay, here gamma unit weight. Okay, so QU equal to 1078.29 kilonewton per square meter, right? Okay, so this is the Q ultimate. Okay, but you have to calculate the load. Okay, the allowable load. So the allowable load per unit area, okay, equal to QU divided by FS. Okay, FS is the factor of safety. Okay. Okay, sekejap. Hello? Ya, ya. Tak boleh? Oh, dah terkeluar eh? Alamak. Okey, sekejap. Keluar lagi. Okay, sorry. Saya punya laptop ke saya punya apa ni masalah ni. Sekejap saya share sekejap. Hello? Hello? Ada, kat mana kita? Kat mana kita tadi? Ni dah kan? Ni dah. Okey, dah. Sampai sini je. Hilang terus. Aduh. Okey. Okey. So kita start balik lah. Alright, so okay, from here we can determine NC, NQ and gamma. Okay, from the table. Okay, so we refer to general shear failure table. Okay, for square foundation. Okay, so we get 25.13 for NC, we get 12.72 for NQ, and we get 8.34 for N gamma. Okay, and then C. Okay, so the given data is C equal to 20. Okay, just put it the value. Q, what is Q? Q is the surcharge. for Q times df. Df is 1.5 meter. Gamma is 16.5. So 1.5 times 16.5 for Q. Then gamma equal to 16.5. Okay. And then you calculate. Okay, using this equation, then you get. Okay, Qu equal to 1078.29 kilometer per square meter. Alright, so you get the value of Q ultimate. Okay, but the question asks you the allowable load, the Q capital, right? Q capital, not this Q. Okay, so from the ultimate bearing capacity, you can calculate the allowable bearing capacity. Okay, so this is the allowable bearing capacity equal to Qu, this Q ultimate divided by factor of safety. Then we got 359.5 kilonewton per square meter. This is Q allowable. Okay, not the load. So how to calculate the load? So the load equal to, okay, 359.5 times B square. Okay, B square equal to 359 times area. Okay, because Q, okay, because Q allowable equal to allowable load, okay, divided by area. Okay, so the area is 2 times 2, right? 2 meter times 2 meter. You want to calculate the Q, the capital Q, right? So that's why Q allowable times the area. Okay, very simple, very easy example. Okay, to calculate the allowable gross load. Okay, so this is the example. Okay, so this is example of the street foundation. The street foundation. Okay, for the street foundation also you can use the Terzaghi bearing equation. Okay, it's placed at depth of 1.5 meter. So 1.5 meter is df. Okay, and then this is 2 meter is the width. Okay, B. C 10 kPa, friction angle is 26, gamma is 19. Okay, determine the maximum wall load. Load mean Q lah. Q. Okay, that can be allowed on the foundation with a factor of safety of 3. Ni pun sama lah. I think same method. Okay, assuming general shear failure. Okay, so this is the equation for street foundation. Okay, for general shear failure. Okay, from table. Okay, refer to friction angle 26 degree. Then you can get NC, NQ, and gamma. And using this equation, okay, you can get 287.6 kilometer per meter square. So therefore, the maximum allowable load equal to 287.6 times 2. Okay, calculating the size of the foundation. Alright, from the bearing capacity from the given data, you have to calculate the size of the foundation. Right. Okay. Okay, a design requires placing a square foundation. Okay, so square foundation is B square, right? B times B. Okay. At 1 meter depth. Okay, at 1 meter depth, so 1 meter is df. Okay, to carry a column load of 1500 kilonewton. So 1500 kilonewton is Q. Okay, the soil properties are C prime 15, phi prime equal to 24 degree, gamma 18.5. What should be the width of the foundation? Right. So it means that this is Q. This is Q. Allowable lah. Okay. This is Q allowable. Okay. Okay. So because the foundation is square shape, so you can use this equation. Okay, refer to friction angle and refer to the table. You can get NC and Q and then N gamma, and then solve the equation. Okay. Okay, you cannot solve the equation because you don't know what is the width of the foundation. Right, so this unknown B. So Q allowable equal to QU divided by Fs, and then so we get this equation. The applied pressure to the ground is, okay, so this is the applied pressure. Okay, so therefore the applied pressure equal to 17.5 B plus 222.1. Okay, by try and error or use the graphic calculator, B equal to 2.4 meter. Okay. Okay, so this is for the square foundation. Okay. Okay, do you know how to get 2.4 using calculator? Or you just try and error? Huh? Anyone know how to get this value? Okay, using calculator. Ada tak yang tahu? Ada yang tahu tak macam mana nak selesaikan? Macam mana dapat 2.4? Tak ada. Tak tahu kan? Tak tahu. Belajar You tengok YouTube. Okay, macam mana nak ni? Okay. Saya tunjukkan satu lah Mungkin awak boleh guna lah jugalah. Okay. Dalam menggunakan Excel lah Dalam menggunakan Excel. Okay, so okay, we use this equation. Okay, we use this equation. Okay. In the Excel So if we simplify this equation, the equation becomes, macam mana ni equation ni? (17.5) equals to 3 plus tambah 2.1 B square. Okay, B square minus equal to 0. Alright, so this is the equation. Okay. Okay, by using Excel okay, here this is okay, so very simple. Okay, so this is the value of B. Okay, you put here for example here you just put 1 Okay, you put 1 because you don't know the exact value for B, and then this is the equation. Okay, this is the equation. So if you see here, okay, the equation is 17.5 B power 3 plus 222.1 times B square minus 1500, right? So this is the equation. Okay, so this is the equation. So if you use B equal to 1, okay, you can get minus. Okay, you can get minus. Okay. Right. So how to get zero actually? Because the equation here becomes zero. Okay. If you try, for example, two. Whoa, you get 471, right? Or you try 2.13. So you get 323. Okay, you try 2.6, for example. Oh, you get 320x. Right. So it's quite difficult also using Excel, right? But I will show you the the fastest step, okay, how to get the B value, okay, using Excel. Okay, you go to data. Okay, you go to data. Okay, you go to the data, and you go to the what if analysis. Okay, you go to what if analysis, and you click the goal seek. Goal seek. All right. Okay, you have the goal seek here. You want to set this value equal to 0, right? To value 0, because in this equation, okay, if you see the equation, the value is 0. What is the value of B? So that's why we set here this equation equal to 0. By changing cell, okay, by changing this cell actually, because we want to calculate what is the B value when the equation becomes 0. Okay, by changing cell, okay, you click this cell. Okay, then you click OK, and then it will calculate for you. Then you can get the answer. The answer here 2.384435 meter. Okay. Okay. So you get the answer here 2.38. Okay. The answer here is 2.4. Okay. Boleh? Senang kan? Tak susah kan pakai Excel? Pakai calculator, awak cari Google lah. Tengok macam mana cara nak selesaikan masalah. Saya rasa boleh boleh gunakan calculator tu. Okay. Depending on the model of your calculator. Right. Okay. Okay lagi tak? Boleh lagi ke? Boleh lagi? Boleh lagi. Ni faham tak? Setakat ni okey? Setakat ni okey? Ada yang tak faham? Okey, faham. Bagus. Okey. Kalau okey saya nak sambung sikit lagi lah. Dalam setengah jam lagi lah. Kita stop pukul 4 lah. Okay, sikit lagi. Okay. Alright. Okay, effect of water table on bearing capacity equation. So if you refer to the previous example, okay, there is no water table, right? The water table is located far from the ground surface. But what happens if the groundwater is close to the ground surface, right? So, okay, in this case, right, so you have to modify the equation in terms of surcharge and unit weight only. So we have three cases here. Case number 1, when the groundwater table is located above the base of the foundation. Okay, so this is case number 1. Okay. Okay, this is the equation for square foundation, right? For the general equation. Okay, case number 1. If D1 less than DF, okay, more than 0. Okay, so means that the groundwater table is located between the ground surface and the base of the foundation. So this is case number 1. Alright, so what you have to do, okay, you have to modify in terms of surcharge. Q is the surcharge. So what is the surcharge? Surcharge is the soil okay Surcharge is the stress due to the soil from the ground surface until this layer. Okay, so Q equal to gamma dF, right? Okay, so this is gamma dF. Okay, so you have to calculate the stress here. So if you still remember how to calculate the stress here at this point, okay, from the ground surface. Okay, from the ground surface. Okay, from the ground surface. How to calculate? So you have, here you have gamma dry, right? Here you have gamma. Here you have gamma saturated. Right. So how to calculate the stress? Exactly the same level of the base of the foundation. So gamma times D1. Okay, gamma, this is gamma dry, gamma times D1 here plus D2. Okay, this is the thickness of this layer. Okay, D2 times gamma prime, gamma prime. So actually this is gamma saturated minus gamma water is the gamma prime. So this is the surcharge, okay, Q. And then gamma, okay, gamma also we have to use gamma prime. Okay, we use gamma prime for this case. Okay, because the base of the foundation is located below the groundwater table. Okay, so that's why we use gamma prime here. Okay. Case number 2. If D is less than B. Okay. D less than the B. B is the width of the foundation. D is the location of the groundwater table. Okay. Okay, underneath the foundation. Okay. So what we have to modify? So same with the case number 1, we have to modify the term Q. Okay, surcharge. So how to calculate the surcharge? How to calculate the surcharge? Okay, the surcharge is until this point, until this point only, not to this point, until this point. So if the groundwater table is located here, means that this is gamma dry because there is no water here. So we use only gamma dry. Okay, gamma dry times dF to calculate the surcharge. Okay, you see here, we use gamma dry, right? We use gamma dry because water table is located here. The condition here is dry. Okay, and then we use dF. Okay, the whole depth here. And then the gamma, what is gamma? Okay, you have to use this equation to calculate the gamma bar. Okay, gamma bar. You cannot use gamma dry. You cannot use gamma dry. You cannot use gamma prime. So you have to use this equation. Okay. Case number 3. Okay, when the D, okay, the location of the groundwater table is more than the width of the foundation, so no effect on the ultimate bearing capacity. So you can use directly this equation. Okay, no need to modify this equation. If D here, location of the water table is more than the width of the foundation. Okay. Okay, no effect on ultimate bearing capacity. So actually how to derive this equation? Gamma bar. Okay, so if you see here, okay, gamma bar equal to gamma D. Okay, actually we want to calculate Uh, oh, you cannot see here, right? Okay, actually you want to calculate the stress until this point. So the stress is gamma D. Gamma D is the dry, right? This is dry because it is located above water table. So we use gamma D because it is D. Okay, and then you have to calculate the stress from the ground table to this point. So plus gamma prime B minus gamma prime D. So gamma prime D minus gamma prime D is actually like this, because this is the distance from here to here is B minus D. Okay, because this is the B, the width of the foundation. Okay, minus D. This is D. So you get the distance here. The distance from here to this point. You get B minus D. Because this is located below the ground table, so you have to use gamma prime. So actually, times gamma prime. So it becomes B gamma prime B minus gamma prime D. Okay. Okay, and then after that, you simplify the equation. Okay. Okay, divided by okay. Simplify the equation and then divided by B. Okay, this equation you divided by B is become gamma prime plus D over B, gamma minus gamma prime. Okay, so you get this equation. Alright. So this is the modification that you have to do if the water table present in the foundation, very close to the foundation. Okay. Okay, so I think okay, this is the Zagi bearing equation. I think we continue next week. So we stop until here. Okay, we stop until this exercise. Okay, for today. This is the last exercise. There is no solution. Okay, so okay, try to answer this. Okay, a column foundation is 3 meter times 3 meter. Given the F is 1.5 meter, this is the F. Friction angle equal to 25 degree. C equal to 70 kN per meter square. Using Terzaghi equation and assume the general shear failure and use Fs equal to 3. Okay, determine the net allowable load the foundation could carry. This is question number 1. Question number 2, if the ground water table rise to the ground surface, okay, if the water table move up to the ground surface, estimate the permissible load. Okay, permissible load equal to allowable load lah. Okay. And then question number 3, if the groundwater table drops down to 2 meter underneath the base of foundation, predict allowable load changes. Okay, so air ni dia drop ke bawah 2 meter from the base of the foundation. Bukan 2 meter daripada sini 2 meter from the base of the foundation. Dari sini ke sini 2 meter. Okay, so predict allowable load changes. Okay, so this exercise is related to the effect of the groundwater table. Okay. Okay, so awak kena buat sekarang lah kot ni. Okay, try buat sekarang. Yeah. Yeah, I know. You don't have this slide. Okay, or you want to do later. I'll give you the slide and you do it later. So I think I can give you this exercise as your first assignment. Okay? Your first assignment. Very easy. Okay, and then after that, I think for the Meyerhof, this is the general balance equation. I think we will continue next week. Okay. Okay. So, any question from you? General equation for Terzagi. Okay. This equation. Which? Yes. The unit. Yeah, the unit is supposed. Okay. Here, this slide or the other slide. Here. Sorry. Which one? Which one? This one. 22. Okay. 22, right? Okay. Yes. Yeah. Kilonewton per meter square. Yeah. Per cubic meter. Gamma is the unit weight. Meter cube. Yeah. Oh, really? Okay, that's it. Okay, okay, okay. My mistake actually. Which one? This one, right? 29. Okay. Which one? 30. Okay. Which one? Sorry, sorry. Which one? Yeah. Yeah. The question is square. Yeah. 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 This is the capital Q. Okay, this is the capital Q. Q Lauber. Okay. Yeah. Mm. Okay. Clear? Alright. Alright. So actually we have one slide. I will because I will update the slide. A bit after I update, I will upload in the author and then you can download using author. Okay. So I think you can solve this equation, this exercise, and you can submit tomorrow. Is it okay tomorrow? Very simple, right? Very simple exercise. Tonight also. Okay. Oh, next week lama sangat tu. Okay, Thursday, Thursday. Okay, this Thursday. Thursday is holiday, right? Today is holiday, so it's okay. Just submit before 12 p.m. on Thursday. Alright. Okay, so any other question? No. Okay, so far so good. So okay semua. Dia faham semua? Senang kan? Quite easy. Quite easy, right? Okay. Right. So okay, record So I think that's all. So thank you very much. Okay, for your attention. So if you have any question regarding the chapter 2, okay, we can discuss in using WhatsApp group. So I think that's all. Thank you very much. See you again next week. Okay, Assalamualaikum. Alright. Salam. Hey. Ya dah close je. Oh, laju je budak-budak ni. Ada. Bukan lah. Jom lah. Jom makan dia.
Kakak kau tu dah bibik pula. Dah makan tu. Tak tengah tu.